Medieval aquamarina are functional sculptures used to pour water for hand washing. The largest group of surviving aquamarina are in the form of lions, already considered to be the king of the beasts in the Middle Ages. Others represent the struggle between Samson and the lion, horses, knights on horseback, and such fantastic beasts as dragons, unicorns, and griffins. They have two openings, one at the top used for filling the vessel with water, and a spout in the mouth or in the chest for pouring. Aquamarina were used in church for ritual hand washing during Mass, and were also used at the dining table in secular life. Aquamarina are among the most imaginative and fascinating objects of the Middle Ages, and have been sought by art collectors since the 19th century. Most were made in Germany, and they range in date from the 12th through the 15th century. At the Metropolitan Museum of Art, which has one of the world's most important and varied collections, they can usually be found in 3 different locations: in the medieval art galleries, in the Robert Lehman wing of the museum on Fifth Avenue, and others as part of the collection of the Cloisters, the Metropolitan's branch museum in northern Manhattan. The exhibition provides an opportunity to bring all of the museum's examples together with additional pieces borrowed from other collections. The exhibition provides a rare opportunity to study the development of aquamarina as well as their function, meaning, and technique. This video focuses on the casting of a reproduction of one of the earliest aquamarina in the museum's collection, probably made in Germany in the 12th century. This example, in the form of a lion, is just over 8 inches high and weighs about 4.5 pounds. It came to the museum in 1964 from the noted collection of Judge Erwin Untermeyer, but nothing is known of its earlier history. The sophisticated use of simplified forms and the alert posture of the lion give the work a great deal of charm.
The emergence of aquamarina in the 12th century in northern Germany and Lower Saxony marked a significant advance in the casting practices of Western European metalworkers. As both vessels and distinct sculptural entities, aquamarina combined function and artistry. In order to satisfy such dual purposes, each aquamarina had to be hollow and cast in the round, a form of casting unknown in the West since antiquity. The unique position of aquamarina in the technical history of metal casting made it an appealing area for study, and to that end a variety of resources were utilized in their examination. X-radiographs clarified aspects of manufacture, such as the shapes and detailing of the cores, the locations of core pins and plugs, the presence of armature elements, the extent of cast-in repairs, the thickness and porosity of the metal, the occurrence of either hard or soft solders, as well as possible later restorations. Microscopic examination of interior and exterior surfaces revealed details of fabrication, such as casting artifacts and the shapes of the tools used to punch or engrave surface details, as well as the minute traces of investment in core material, polishing compounds, and pigmentation, which were identified and characterized using the scanning electron microscope, polarized light microscopy, and X-ray diffraction. The compositions of the metal alloys used in casting the aquamarina were determined by inductively coupled plasma mass spectrometry. Additionally, surviving medieval and Renaissance manuals and treatises were a valuable resource. The principal medieval text is the 12th century treatises on diverse arts, authored by the Benedictine monk Theophilus. It is the only surviving manual outlining medieval metalworking practices, and while it is unclear if Theophilus was a practicing goldsmith or metalworker, there is general agreement that his recitations on metalworking techniques are very closely observed and generally in close agreement with the physical evidence retained by the objects.
What has become evident in our research on the technological and creative aspect of aquamarina is that alchemy was an essential part of the medieval world of the metalworker. Theophilus' knowledge of alchemy is reflected in many of the working processes described in his treatise. At one point, even going so far as to adopt the symbolic language of the alchemist in order to preserve his secrets only for the adepts. Modern historians have often misunderstood Theophilus and at times described his passages as the lurid and garbled language of alchemy. To better understand medieval metalworking, we must leave our modern biases behind and acknowledge that alchemy was an essential part of the craftsman's life. Alchemy was much more than the transmutation and making of gold. It encompassed all of the arts that work with fire. For the medieval craftsman, it was through the alchemical processes that the substance of nature could be separated, isolated, manipulated, and reunited in a more perfect way. Historically, the Egyptian god Thoth became the mystical figure of Hermes Trismegistus, who was considered the patriarch of alchemy and the source of all wisdom. Egyptian and Greek alchemy did not pass directly to the Western medieval alchemist, but was filtered through an extremely important intermediate links, the Arabs. It was through the Arabian philosophers that ancient Hermetic doctrines and alchemical processes were preserved, and many of the early technical achievements of Islamic lost wax castings were a reflection of their great alchemical knowledge. From the second half of the 8th century, the time of the famous Arab alchemist Jabir ibn Hayyan, known in medieval Latin Europe as Geber, Arabic alchemy theorized and effected the formation and refinement of metals, the preparation of steel, and of many other related substances, all of which became essential for the making of the aquamanillia. The Persian alchemist Al-Biruni, writing in the 11th century on the making of brass, described how to collect the zinc oxide tutia from the fumes in their furnaces, and, in his own words, how copper is made yellow until it becomes like gold. Europe's indebtedness to Islamic casting technology and brass making cannot be fully understood outside the context of Islamic alchemy. By the 12th century, Islamic alchemy was readily available to the Latin West through the translations of Arabian alchemical treatises. By the 13th century, some of the most fertile minds and prominent Christian philosophers in the West were among the great alchemist figures of the time, from the Dominican monk Albertus Magnus to the Franciscan friars Roger Bacon and Ramon Lull. For Albertus Magnus, alchemical knowledge was no longer based solely upon the Aristotelian philosophy on the nature of metals, but included the close observation of the qualities of substances and the use of all of our senses. In his own words, metals were liquefiable and malleable, their colors, their taste and odors, their ability to be consumed by fire. He also directly observed and transcribed the everyday sensory experience of the medieval metalworker. Roger Bacon asserted that there were two kinds of alchemy, speculative and practical, and he emphasized that the practical was used by craftsmen and artists and that all of the arts depended upon it. Practical alchemy was only a branch of a larger, more comprehensive philosophical system. Alchemy for the Islamic, Jewish, or Christian alchemist, apart from the practical aspect, was also a religious, mystical, and speculative search. The alchemist's myths, legends, and experiments, no matter how scientifically wrong they appear to us today, were just as credible to the medieval metalworkers as the lions, the dragons, and other beasts depicted in the Aquamanillia. They were his major source of knowledge. Although it was practical alchemy that allowed the making of the lion Aquamanile, it is to the mystical aspect of alchemy that we must also look to better comprehend this creation.
In his treatises, Theophilus describes many of the substances and materials used by the medieval craftsman in his daily work, most of which could be obtained from his immediate surroundings. The recipes Theophilus used to convert these substances range from the simple and familiar to more complex processes best understood within the context of practical alchemy. Beeswax was the essential ingredient of lost wax casting and was easily separated from the honey in the comb. It was a valuable commodity, in some cases even used as currency, and its production expanded to satisfy the demands of local foundries. The medieval sculptor could modify the beeswax to his liking. With the addition of pigments such as cinnabar, details worked in the wax were more easily read. According to the type of modeling or carving intended, the wax could be modified by adding oils to increase its softness or hardened by adding pitch and other substances. For large, hollow castings, such as church bells and tripod pots, tallow was often substituted for the more expensive beeswax. Using methods known since antiquity, tallow was easily rendered from animal fat by melting over low heat and then straining into a bowl of hot water. As the water cooled, the tallow solidified on the surface. As the process was repeated, the tallow became whiter and harder. From the skins or hides of animals, the medieval craftsman could extract various glues. Indeed, every part of the animal was put to use, with even their bones and horns burned to obtain bone ash. By washing, drying, crushing, and sifting burned wood ashes, they obtained a perfect refractory material. Pitch was extracted from resin secreted from the barks of pine or spruce trees by evaporating off its associated oils over a bath of hot water. The sediments left in the wine barrel during fermentation were burned to produce argol, or tartar, today called cream of tartar, perhaps the most versatile substance in the workshop and used for pickling and as a flux for soldering or melting metals.
Not all materials and substances described by Theophilus were so simple to obtain. Some require complex alchemical processes such as sublimation, distillation, fermentation, cementation, and calcination to separate out single elements and reassemble them in a new and perfect alchemical order, utilizing a variety of apparatus, furnaces, and vessels. These mineral specimens of cinnabar are from Almad in Spain, where cinnabar has been mined since pre-Roman times. Chemically, cinnabar is mercury sulfide, used since antiquity as a pigment and as a primary ore for mercury, with both forms used in the manufacture of aquamanila. The pigment could be isolated by grinding the mineral crystal and then washing it to segregate the pigment from the less heavy residue. The extraction of mercury or quicksilver was mainly obtained by distillation in a process described by ancient authors such as Pliny and often illustrated in Renaissance treatises, as in this figure by Agricola. Mercury was used by the medieval metal worker in a multitude of ways. When combined with gold, it formed an amalgam that could be applied over other metals such as silver, copper, and brass to fire gild them. Once coated, the object was heated over coals to evaporate the mercury, leaving a layer of pure gold bound to the surface in a process described by Theophilus in great detail. Theophilus did not have the chemical knowledge that cinnabar was mercury sulfide, but he was able to describe the manufacture of artificial cinnabar, known as vermilion. Take sulfur, break it up, and add 2 equal parts of mercury. Put them into a glass jar, then bury it in blazing coals. You will hear a crashing inside as the mercury unites with the blazing sulfur. The medieval alchemist, since Geber, believed that mercury, symbolized by the eagle, and sulfur, symbolized by the dragon, were the basic and major elements, the prima materia, of the great work, the Opus Magnus, having the power of dissolution and hardening, solve and coagula. In the Aurora Consurgens, this argument is illustrated by the analogy of the alchemical process next to the baker, whose prima materia is simply water and flour. This alchemical union of sulfur and mercury in a glass jar, described by Theophilus, is also symbolically represented by the 9th century Arabian alchemist Ar-Razi. Here we can see and almost hear the struggle between the dragon, who represents sulfur, and the eagle, who represents mercury. The 4 flowers held by the dragon's feet are the 4 Aristotelian elements of nature, air, water, fire, and earth, that they struggle to manipulate. The influence of alchemy on medieval artists were not just practical, but mystical and spiritual as well. The coexistence of the practical and spiritual is expressed in an anonymous 15th century alchemical manuscript that appears to have been written by a craftsman who identified himself as Gratheus, probably from a region in the Lower Rhine. By writing in a vernacular instead of Latin, Gratheus appears to have directed his manuscript to other craftsmen alchemists rather than to the elite academics. Gratheus also introduced the reader to a series of symbolic images to guide the readers through the difficult alchemical processes by way of figurative metaphors, some of which are associated with Christological images. We can see that alchemical vessels form the halo surrounding the head of Christ, and the scene of the resurrection of Christ becomes a symbol for the alchemical process of sublimation. For the alchemists, it was through fire that metals could be separated, united, and transformed. The late medieval alchemists even forged a new word, crucibulum, derived from the Latin word for cross, to describe the vessel, the melting pot that made this transformation possible. In English, the word remains crucible, in Italian crucibile. Among the alchemical symbols, the cross became associated often with the crucible. The duality of alchemy expressed by medieval alchemist craftsmen such as Gratheus confirm for us that sublimation, distillation, sedimentation, or calcination were more than just practical processes. They were also mystical and philosophical transformations that apply to their lives and their arts.
Due to the lack of written documentation, the artists and craftsmen that created medieval aquamarina are mostly unknown to us. What is clear is that metalworking knowledge was but one of the many skills needed in the process of creation. From the first spark of conception, the artists had to adjust, modify, and fine-tune their ideas and ambitions to accommodate their technical casting skills and the limitations of their time. Our lion, as with all of the medieval aquamarina, was cast in the direct process of hollow lost wax casting, where the sculptor first built up a clay core to approximate its eventual size and shape. The basic material for the core was clay, the composition and fabric of which varied according to workshop traditions and locations. Theophilus' recipes called for a simple mixture of clay and dry dung. By the Renaissance, Biringuccio and Cellini's clays were tempered with small particles of hay or straw, wool cloth clippings, ashes, coarse sand, and finely ground iron rust, beside the usual horse, donkey, or cow dung. Technically, these additions imparted a degree of porosity and plasticity to the core. After its firing and during the pouring of the metal, the organic material carbonized or burnt out, often leaving small, empty cells within the baked clay core. These minute voids allowed the core to compress as the metal cooled and contracted around it, as well as allowing some of the entrapped gases to escape. Due to its small size and simple form, the core for this line did not require an armature for support. However, in some of the more complex aquamarina, the X-radiographs indicate that wire armatures were incorporated, either selectively or as part of a larger, more extensive framework.
The core was the true genesis of the aquamanile, and in its modeling the artist was processing a kind of alchemical distillation. The core was the essence of the lion aquamanile in its purest form. In the book of Genesis we read, "The Lord God formed man out of the clay on the ground and blew into his nostrils the breath of life." It is no coincidence that to this day the Italian word for core has not changed from the Latin word anima, that translates as the soul, the breath of life. During the core's modeling, the sculptor had to foresee and keep in mind all future steps in the casting process. For instance, the rounded corners and cavities help to ease the flow of the molten metal and reduce the turbulences associated with the pouring of the metal. The core was dried or in some cases baked before the next step of applying and modeling the wax. It is during the application of the beeswax that the artist could and did impact the unique and distinguishing characters of the lion. While carving and modeling details, the artist transformed the core from a tabula rasa and pure soul to a corporeal and physical lion. We should keep in mind that every detail and nuance he put into the wax in the final stage of casting would be accurately and entirely reproduced in metal, including its thickness. A fairly uniform thickness of the wax helped to maintain a steady metal flow during the pouring, as well as an even cooling phase for the metal to prevent it from cracking. The coloring of the wax with cinnabar may have had strong alchemical connotations. Although no documentary evidence of medieval red waxes exists, surviving Renaissance models attest to the use of this color. In alchemy, the red, known as rubedo, like a ruby color, is the third phase of transformation. It was also known as anima tingenti, the tinting soul, because when the soul, like our lion's core, is introduced to the innermost part of the body, it gives the red color, life and blood to the body.
In casting a brass censer, Theophilus described a simple and efficient way to obtain a smooth and even thickness of wax. By using two strips of wood, attached parallel to one another on a broad plank, the molten wax could be rolled out or poured to a specific thickness, with water easing its release. In examining the Aquanilia in the exhibition, the thickness of their metal walls was discovered to remain remarkably consistent, averaging between 2 and 2.5 millimeters. Theophilus modeled his censer by cutting shapes from the sheet wax and applying them to the clay core. A similar method could have been used for applying a uniform layer of wax onto the lion's core, and indeed a similar system is still used today for large and medium-sized hollow statues created by the direct process. For smaller, lost wax castings, such as the lion, another method should be considered. By dipping its core into a pot of molten wax, an even layer of wax would be deposited over its surface. The process could be repeated to achieve the desired thickness.
Whichever method our sculptor may have used to coat the core, all additional modeling was achieved by carving and adding more wax with brushes or as spatulas in a distinctive modus operandi unique to each artist. In the case of the lion, the sculptor modus was uncomplicated and direct. Sheets of wax were cut into shapes and applied to the body. The handle was shaped independently either by carving a solid wax rod with warm tools or braiding together two strips and then integrating them to the whole. The lion's entire mane was obtained by the simple method and by the use of a single shaped spatula. The tail and other details were similarly created by applying strips of wax. The lion legs would have been modeled in the core originally to facilitate the sculpting and the desired proportioning of the overall form. During the application of the wax, the legs were broken off, the stubs shaped, and wax rods substituted as the initial building block for their shaping.
It is difficult to determine if incised details, like the tufts of the lion's mane, were originally carved in the wax and then recut after casting, and which details were directly engraved into the cast metal. Certainly, engraving all of the lines initially in the wax would have facilitated their later finishing. By hardening the wax, the sculptor could ease its carving and enhance the chances of the wax model retaining delicate details, free of distortions due to subsequent handling and finishing. An opening at the top of the lion's head was cut out and hinge loops formed during the wax modeling to provide an opening for filling the aquamanilia with water and a point of attachment for the separately cast lid. The holes for the hinge and the spout would also be worked into the wax by inserting wooden dowels or reeds which would carbonize during the wax burnout and the curing of the investment. Molten metal was prevented from filling the hinge loops during casting. The openings in the head and in the belly would serve later, after casting, for the removal of the core. When the wax model had been finished to the sculptor's satisfaction, a number of metal pins would be inserted through the wax and into the core. The core pins were cut from sheet metal, either iron or copper alloy, and tapered into points for insertion through the wax layer and partial insertion into the core. A significant portion of its length was left protruding from the wax to be enveloped and secured by the overlaying clay investment. When the wax was melted out, the core pins secured the register of the core within the investment and prevented it shifting, either during the baking and curing of the core and investment or while the molten metal was being poured.
The gating or spruing system was comprised of runners and risers. A gating system of wax rods would be attached to the wax model for the eventual delivery of the metal. To better illustrate and emphasize their distinct roles, we have kept the wax rods for the runners red and colored the wax rods for the risers in blue. The gating system can be compared to the circulatory system of veins and arteries. In the casting circulatory system, all of the rods for the runners started from a central funnel-shaped basin. From this reservoir, once the wax had been eliminated, the runners delivered the flow of molten metal into the various cavities left by the burned-out wax. The risers instead helped the air and gases trapped in these cavities to escape. Not surprisingly, many of the solid and thicker elements of the lion's features, like the eyebrows, tail, and endos, were carefully and aesthetically orchestrated by the artist to function as additional conduits to supply the flow metals to the right area, and using every advantage to achieve a good and sound casting.
The proper sizing and positioning of the gating system was a critical and crucial step for a favorable outcome to the metal casting. We can assume that every sculptor or caster had their own secrets and methodology for positioning these gates. The one shown here is one of the many possible arrangements. The prevalence of partial casting failure in many of the Aquamanila in the exhibition suggests that their arrangement of risers and runners may not have been thorough enough.
The fully gated wax model would be invested in a refractory material in preparation for the baking and elimination of the wax. To retain the finest details of the wax model, the first few coats of clay were grounded and sifted to create a fine slip consistency that would be carefully brushed over the wax. Each coat would be allowed to dry just enough to become stiff to the touch, then a few more coats added and let dry. Theophilus does not specify the exact composition of these preliminary layers of clay, but suggests that they be thin and well sifted. However, in the Renaissance treatises of Biringuccio and Cellini, many other ingredients are added to this first layer, such as wood ashes, ashes from the horns of oxen and rams, iron rust, tripoli and other iron oxide, pumice powder, and so on. These ingredients were widely used by the medieval metalworker, and although Theophilus does not specifically describe them in relation to his lost wax casting, he uses them in other processes. Layers of coarser refractory clay were applied over these initial coatings, with each layer allowed to partially dry. We have assumed that a cage-like wire structure was embedded in the clay as a reinforcement before the final layer was applied. Once the mold was completely dry, it was placed near the fire in order to allow the heat to melt the wax, a precious commodity whose recovery was essential. The core and the investment would then be cured and the wax completely burned out by firing it in a furnace of sufficient diameter to allow charcoal to be placed between the interior walls of the furnace and the walls of the investment.
The predominant metal used for casting aquamanila and other medieval objects was a copper alloy, referred to as Latin, containing zinc as the principal alloying element, with tin and lead present at levels greater than 1%. The raw materials making up the alloy were readily available to the workshops in Lower Saxony, northern Germany, and Nuremberg, which produced aquamanila. Raw copper was supplied to the metalworker from the mining sites. The zinc sources were roasted calamine, either smithsonite, a zinc carbonate, or hemimorphite, a zinc silicate, and tutti, zinc oxide, derived as the byproduct from the smelting of lead ores. There was no recognition that calamine, described by Theophilus as a kind of stone of a yellowish color, sometimes reddish, or tutti, contained zinc, and indeed zinc was not identified as a metal in the West until the 16th century. Its appeal for the metalworker was that it produced an alloy suitable for casting and engraving, and imparted to the copper a yellow color close to gold. As described by Biringuccio, brass is copper given yellow color by art. Surely it was a splendid discovery for which we must thank the alchemists. Gerber, perhaps the most renowned of Islamic alchemists, acknowledged the importance of tutti by including it as a component of the philosopher's stone. In our replication, 2 volumes of charcoal were added to the crucible as a reducing agent, along with 1 volume of roasted hemimorphite and 1 volume of raw copper coupons. Initially, a volume of charcoal was ground with the hemimorphite and placed in the crucible. The copper strips were then placed above the zinc and covered by another volume of charcoal. The lid for the crucible was sealed with clay and the whole placed in the furnace. The zinc and copper were alloyed with one another in a cementation process, which could occur either in open or lidded crucibles. The hole in the crucible lid allowed the color of the charge to be monitored and the contents stirred. The volatilization of the zinc was perceived to have been initiated when a white vapor was emitted, at which point the hole was sealed to retain the zinc in the crucible. As the temperature rises within the crucible, the zinc, which has a melting point well below that of copper, vaporizes and is absorbed by the solid copper, progressively altering its composition. When the melting point of the continually forming alloy of copper and zinc is reached, the metal is allowed to cool, and if necessary, the process repeated to obtain the desired physical properties. At a temperature close to the melting point of the forming alloy, the crucible was removed from the furnace and examined. The metal coupons had a visibly golden sheen, similar to brass. They were returned to the crucible along with more charcoal and melted to homogenize the alloy. Analysis indicated the alloy had a zinc concentration of 15%. Crucibles had to withstand the high temperatures required for forming and melting a range of different metal alloys. Theophilus recommends using a mixture of 3 parts raw clay and 2 parts of grog, comprised of fragments of earthenware vessels and crucibles crushed together. A shaped piece of wood served as a form and speeded production. Once air-dried, the interior surfaces of the crucibles were dusted with wood ash and fired in the furnace.
Simultaneous to the curing of the investment, a sufficient quantity of brass would be melted to fill the space previously occupied by the wax. When the investment cured, it was removed from the kiln and while hot, buried to the levels of its pouring basin in a well-tempered soil, which provided additional support for the investment to keep it from breaking up under the pressure exerted by the gases and steam generated during the pouring of the molten metal. The earth would also insulate the core and the investment against the loss of retained heat, providing an advantageous environment for the flowing of the metal. Once the investment was prepared, excess charcoal, which helped to contain the zinc vapors, was removed from the top of the crucible and the molten metal poured over a stick wrapped in cloth that would help to reduce any oxygen within the melt and restrain any dross associated with the metal in the crucible.
When cooled, the investment was removed from the earth and broken away. The gating system was cut off as required, and the surface of the lion carefully exposed and inspected for flaws. Larger casting flaws were generally repaired at this time with cast-in fills, similar to those on the original lion's buttocks. Interestingly, even with our extensive gating system and our pre-knowledge of the existing flaws, our casting replicated the flaws of the original. Smaller voids might be filled with blanks, shaped to size, and hammered in. The core pins were generally knocked out and filled with copper plugs, hammered in without the addition of solder. Their presence was disguised by working the surrounding metal over their exposed surfaces. The transformation of the raw, as-cast surface to its finished state follows closely the description Theophilus gives for finishing his cast censer. First file across all the grounds, using various files, square, triangular, and round. Then engrave them with engraving tools and scrape them with scrapers. Finally, clean the work all over with sand and sticks whose ends are slightly shredded. The extent of finishing required would vary depending upon not only the skills of the caster, but also on the vagaries of chance and good fortune. Since most aquamanila were not gilded, and there are no records or receipts for their finishing, nor any preserved original surfaces, we are left to presume what their final surface finish might have been. Apart from sand, which would dull and scratch the surface, Theophilus also recommends a variety of other polishing compounds for metalwork and enamel, including finely scraped chalk, a soft black stone mixed with saliva, and sandstone, followed by ground-up potsherd and saliva. Any combination of these compounds and others could have imparted a reflective sheen to the metal.
Just as the medieval alchemist, the creator of the lion Aquamanile isolated, manipulated, and rearranged the forms and elements from the great book of nature. In the genesis of his lion, the artist distilled the form to obtain his essence, the soul. With the modeling of the wax, he gave us his vision of the corporeal lion. Through the pouring of metal and the transmutation of fire, he gave it the breath of life.